Hello and good morning, everyone. Thank you for joining us today. I'm Dr. Chani Rallan, and welcome to this webinar where we will be showcasing the QWater system, which is a decentralized drinking water system, and the AIoT smart water solutions for treating water and wastewater treatment. Both these technologies, which have been developed by the Water Division at ITRI Taiwan. So thank you to all our participants for joining us this morning. For the first session, which will be covering the QWater decentralized drinking water system, we will have Mr. Wei Cheh Jen, who is a researcher at the Water Division at ITRI, and his research focuses on the development and commercialization of decentralized water treatment system for drinking water. William, thank you for joining us this morning, and thank you for presenting this technology. I think you need to turn on your camera, please. Thank you for joining us, and over to you. We look forward to hearing all about this.
Hello, everyone. Yeah, I'm Wei Cheh Jen from the ITRI. Can you see the PowerPoint? Okay. Okay, today I will talk about a topic about a decentralized water treatment system. As for the remote area, drinking water supply. Yeah, and ITRI innovate this system we call QWater. So the first, what is different about the centralized system and the decentralized systems? And you can see this picture. The centralized system, like a conventional water treatment system, we use the calculation, filtration. The final one is the disinfection. So after this process, we will through the pipe and provide the factory, the house, the water use. So in the urban areas, the centralized systems can treat a large volume of the water at a high rate and accommodate all the resident, business, and industrial use. So this process will develop can effectively and provide the tap water to people. So however, the capital costs and the operating the maintenance cost from the centralized systems can be significant. Yeah, it's very high. So it's considered about the water resource development and the construction of the significant fractures, like the treatment facilities, the reservoir, and the water distribution main. And the amount of the monitor and the control systems is cost very high. So if we live in a remote area or the undeveloped area of the population density, maybe the 200 people or some small village, and the way from the village is very far away. So it's not suitable about the centralized systems because the piping or some construction costs may be very high. So we can apply like this picture we call the decentralized system. It's separate like the POE and the POU. The POE means the point of entry. So the system, the water treatment system is before our house. And the POU, the point of use, the water treatment systems in our house. And after the system, we get the tap to our water use or some bathrooms water use. So on the development, under the development areas, there's lack of financial resource or technique support. So maybe they can construct a bigger light system. So maybe we can use these small scale systems to treat the low water and provide drinking water for people. So in ITRI, we try to innovate some new type of the water treatment system, just like we call the QWater. So about why we want to do use, because we know some data from the UN or the WHO, they provide the data. There are the 2.1 billion people at home can get the safe waters, and about the 800 million people, they do not have the basic drinking water service. So every 160 million people directly drinking the surface water like the river, the stream, and the lake. They lead to every 2 minutes, one child will die because they drinking the unclean waters. So why we want to do this? We want to provide the remote areas people get the, and many diseases use the water from the median, so we can see the damage from the central nervous system, virus infection, hepatitis, and diarrhea, and some skin disease. They all because about drinking the unclean water. And why we want to do this? Because we made the big typhoon about 2,000 years. So this typhoon will strike Taiwan and cause some place they didn't get the clean waters. So you can see after typhoon or some disaster, we meet the raw water is high turbidity. And the traditional water system is very big, so we may take many times to installation this or some fabrication. And if we want to transport the system to the remote area, we want to take very many times because the road is broken. And the disaster, but because the electricity is very important in some at the disaster area. So we conclusion some point is one is the road is broken. So the system maybe size will decrease and the weight need to decrease. It's easy to transport. And at the water quality, we focus about the turbidity and the bacteria to the main pollutants. Because after the typhoon, some sand or dirty, so the turbidity will turn to about the drinking waters. So the third is a long installation time. So we need to make an easy installation, like IKEA, like IKEA, we can do by ourselves and easy to assemble it. And the final one is a high power consumption. So how to set up the easy process to energy saving and green. So it's our QWater evolution. So you can see at the 2009, we have the BioM system, but it is for the wastewater treatment systems. So we want to change it, and 2011 we got the first type of QWater. You can see we modularize the systems, and we can build and assemble the QWater in the 20 minutes, and the area just 1.3 square meters, and the weight we decrease to the 400 kilometers. And one day we can provide 15 cubic meters drinking waters. So after 2 years, in order to add the RO membrane, so the QWater have the desalination function. So the building time will increase to 60 minutes because some equipment or some pump will add in these systems. Area is 1.8 meters. And provides water. Okay, so we can see the first type, the QWater. We have why we call it QWater because we features. One is quick. The system is easily to assemble in 20 minutes by 2 persons. The second one is quality. And quality, we can conform to the drinking water regulations with the we can allow the 3,000 use to purity water in our one is just the space on file.
Sorry,
We
William.
provide cleaning water to at least the 60% of the about our water. So we all.
I think your voice is breaking slightly. So can you maybe just go back to the QWater slide, because where you were describing the decentralized system with the different capacities?
Okay. And we will try another Wi-Fi.
Okay, all right.
Oh, sorry about it.
That's fine, no problem. I think this is a great system. I like how you've described it as an IKEA DIY QWater system. So essentially we can build this up in 60 minutes. So it's quite handy to have, especially if we have to set a decentralized drinking water system, which I'm sure most of our participants will also agree that if you have to set this up even in rural areas where we're having the access to build large water treatment systems is a bit difficult.
Mm-hmm. Yeah.
Hello, Jenny.
Hi, Anne.
Yeah, is that clear now?
Yeah, it's clear now. Yep.
Okay. Sorry, so we're back to the previous slide, right?
Yeah, yes, please.
Okay, thank you. Is this slide okay?
Where you're describing the different capacities?
This page?
No, the Q water evolution system. Yeah.
Yes, this one.
No, the one before this. Yeah, this one. Yeah.
This one.
No, the one next.
This.
Q water evolution. Yes, this.
Okay, let's start about the QWater evolutions, okay? So we use the BioMF systems from the 2009, but this system is just for the wastewater system. So you see the building time, you need 3 days, and the area is 12 square meters, and the weight is very heavy. It's 600 kilogram. The quantity maybe the largest 24 cubic meters a day, but it's not easy to transport to the remote area. So we innovate the first type QWater in 2011. You can see the picture is a modular equipment. We modularize the wastewater water treatment systems. So we can easily to build time is 20 minutes. So we have a small area, 1.3 square meters, and less than 400 kilogram. Today, we can provide 15 cubic meters drinking water. After 2 years, we add the RO membrane in our QWater. So it also have the desalination functions, but you need to, building time is increased to the 60 minutes because we have more pump, more equipment inside. The area is 1.8 square meters. The weight is also less than 400 kilogram. One day we can provide 5 to 10 cubic meters drinking water. So let's talk about the first type QWater systems. Why we want to call this systems QWater? Because we have three Q. First one is the quick, and this system is easily to assemble in 20 minutes by 2 persons. Second one is quality, and we can show and confirm these systems to the drinking water regulation with high water turbidity. As we try the test is 3,000 NTU. And last one is the quantity. And we just need a 2.5 cubic meter space and can provide one day 15 cubic meters drinking waters. And it can provide remote areas people at least 60 persons. So let's check the QWater's process. We will use the pump to take the water from the lake, the river, and pump into our systems. So we can see the first one is the incline plant. Why we want to use? Because it have the angle is 60 degrees. So the big dirt or some sand in our systems, it will be intercept from this. So the first one, he have the sedimentation function. So we use the gravity to let the water from this pipe to the second unit's buttons. And the second one is a bionet tank. It's like the PU, this material is a PU sponge. And we got this, the surface area is very big. It's 1,250 square meters from the 1 cubic meters. So they have some smaller pores inside. So we can intercept the small particle and some microorganism from this unit. And we also use the gravity to let the water go through into the third one is a UF membrane tank. We got some hollow fibers PVDF UF inside, and the pore size is 0.08 micrometers, and the total area is 30 square meters. So the bacteria and some small particle will decrease and from these systems. And the final one is the UV light is for the disinfection function. So through this process, we can get the drinking water easily and quickly. So the filtration process is normal used to the drinking water systems because the membrane is the useful and quickly material to want to decrease the pollutant in the waters. So we can see the right side is the material particle size is bigger. So we can see the sand, some large, so the some silt, and clay is a bigger one. So we also use the conventional filtration process. We can decrease this material. So if our pollutant material is smaller one, we can see the humic acid or some virus and small bacteria. We need to use the membrane to take off it. So the micro filtration and the ultra filtration with UF, NF, the nano filtration, RO or some ED or EDR. This is useful from some ions and some cells or virus. It's useful to use this membrane to decrease this. So we add you can see the second type, QWater, you use the RO membrane. To final one to be the desalination function. We also use the personal service. to control these systems. And this system we to use the bionet. The second one is active carbon to decrease some activity material, the carbon. And the third one is the UF membrane. Okay, let's see some video to introduce the second type, QWater. So we can see the raw water is high turbidity, and we just one touch to control the QWater system, and the system will automatically operate. So just needs few minutes later, we can get the safety drinking water. So you can see the turbidity is good, and the volume is increasing. So after the test, we will ask the people to drinking this water. And we can see the experiment times is very easy because we modularize the tank. So we can assemble it one by one. Okay, so this one is we utilize the QWater and combine the cart to increase its mobilities. So you can see it's a ITRI, it's a famous NGO in Taiwan. We use the cart and the water treatment systems to provide the digest areas drinking water. So this one is combined with the boat. So the boat will sailing in the river or the sea, and just to pump the seawater or river water through our system and provide the drinking waters. Okay, so this case is about the disasters relief, but we also do some remote area drinking water supplies application. So you can see from the 2011 to the 2018, is many cases about the remote area application. So first one, we can see the first case, 2011 in Taiwan, Taoyuan City. It's a remote elementary school. It's still operation until now, so it's more than 8 years operation times. We set up the QWater in the remote area to provide the teachers and the students the daily water use, classroom or some dormitory and kitchens water use. So one day is a 2 set of QWater, so it can provide us 30 cubic meters drinking water per day. And the power consumption is very low, it's just 1 kilowatts per cubic meters water. And the maintenance cost is just 1 year's $1,500 USD. Okay, in Taiwan, we also set the QWater and try the green power. So you can see we add the solar cell and the wind power machine to decrease the QWater's energy saving about the 80% energy saving from the QC, the QWater, and the stable auto operation in 8 years. So in the remote area, we can see the big problem is high turbidity water after the typhoon or the big rain. So our system need to equip the high turbidity functions and the far distance between the community. So we need to auto control, auto operation is very important. Another case, we set the QWater in the remote urban and remote village. We use low water resources, underground waters. And we set up this QWater like the water station. And people just through the coins inside, they can get the clean drinking water. And this money, we can save it and provide the people salaries and the materials cost. So we can in charge from this money. So the process is very simple, and we also modularize this system from the scent filtration to RO to UV to get the clean drinking water. In that case, it's in China. It's industrial applications about the ceramic factory or the aquaponic greenhouse water use for the people or some fish or some farm water use. And the big problem is in China, you also know the water is very hot, so we need some different process to treat it. And in this case is in Europe, it's called Poland. We set up this QWater and to get the CE markers because the system want to use in Europe. They ask me, they require me, our ITRI to get the CE markers. So you can see the QWater type is different. And this company is a high potential for the patent transfer because if they buy the system from Taiwan to Europe, they will get the high cost for the transportation. If they get the patent transfer, they have the right to construction this QWater in Europe. So you can see we got the 2 CE certificate is machinery and the low voltage directive. Okay, the final one is the South India. We set up this in 2014. And this area is in the village we call the Tipnet. So we use it to increase the working opportunity because they also sell the money to get the drinking waters. And 1 liter drinking waters, we sell the 0.17 USD dollars. So in the local place, we meet the terrible public hygiene, and the far distance between the community is decreased the transport time. So water is also very hard. The TDS is 600 to the 1,000 milligram per liter. So we share some picture about this. The village is around the Mysore district. Is Karnataka. It's beside the temple. So we designed this system, the modularized system, to draw the raw water resource is also the underground waters, but the process is some different. We use the pre-filter to the active carbon, the UFRO. The final is also the UV. So we transport the system in the local place, and we want to find some car to use it to transport to our need place. So you can see some people in the local place, they will help me to take the systems up and down. So first day, we just set up the system. You can see it's the low water tank. It's the drinking water tanks. We'll go through our system. So the final one, we show the GAC is active carbon. You can see the color is very bad, very dark. So after the UF and the RO, you can remove some turbidity, organism material, and some bacteria to get the drinking waters. Okay, so you can see after our system, many people are waiting to take these waters. Okay, finally, we want to conclusion our Q water. We have the two type Q water and separated from the water production rate. One day we can provide 15 cubic meters drinking water, but they just can remove the turbidity or some organic matters and the bacteria. If we want to meet some seawater or some brackish waters, we need to use the desalination Q water. So this process will sound different. And this one is energy consumption. If the seawater, the consumption is large, is 4 kilowatts per hour. So about the operation cost, so you can take just a reverse. Okay, finally, we also combine the Q water and the IoT. So later, Dr. Rowe will introduce some case about the water treatments and the IoT. So we can collect some data from the monitors equipment to get some data we will collect inside to do some design factor. Okay, it's our report today. Thank you, everyone.
Thank you, William. That was a very interesting and very good presentation and very detailed as well. So at this point, if all our attendees have any questions which they would like to ask, I'm sure people have questions on how the Q water system works. So if you could just please put it in the Q&A box. Okay. Well, I have a question. So, you know, the Q water system, which was applied, I think you put in an example of it being applied at a ceramic factory. Was the main issue there mainly to do with the hard water?
The hard water, we need to add some different process, like the ion exchange, the resin. Yes, we need to take the hard materials first, like the calcium and magnesium. Yes, so because it will decrease the life about the UF membrane or the RO membrane. So the different process is very important.
Okay. And so basically the design of the system you customize as per the inlet water treatment. So as per the water quality of the inlet, then you can
Yes,
customize the
first
design.
we need to know the low water's quality, quantity. Yes, but QWater it can quickly change our unit, like the active compound or just like say the ion exchange resin. Yeah, it can quickly change.
Okay. And can you customize the quantity as well, the size as required? You can customize the actual size required for water treatment capacity?
Yes, yes, we can enlarge the production volume. Yeah, it's more
Okay.
than 15 cubic meters per day. Yeah.
Okay. Okay. It's very good. Very interesting. Do we have any more questions from any of our participants? If you can just put it in the Q&A box. I don't think, I think oh, we've got one here now. We've got a question from Mr. Chandra, who would like to know, can it be used for domestic single household hard water treatment? And what is the OPEX? I'm assuming this is the OPEX cost. Yeah, can it be used for domestic single household hard water treatment? And for 1,000 liter per day, what is the operating cost? The capital cost, Mr. Chandra, we can have a discussion on email regarding this discussion for the CapEx. But for the OPEX, if William, you can give us a bit of an indication. I think you mentioned it as well. William?
Hello?
Oh, sorry.
Sorry?
Can this be used for treating domestic single household hard water?
Oh, we settle this from the drinking water. So if you want to treat the domestic water, so we want to change the type about our system. Yes.
Okay,
Because the domestic
No.
water they have some organic material inside. Yeah, so you need to change some process.
Okay. And what is the minimum size, smallest size of water treatment system?
The medium size?
Minimum size, smallest size.
Oh, we have also the 1 day to provide 5 cubic meters systems, and the size is smaller. Yeah, the size is smaller.
Okay, so that's the smallest system, so 5 cubic
yes.
meters a day.
Yes.
So we've got, that was from Mr. Sehgal from Mayapuri. Then we've got another question from Mr. Devi Rajendran, who would like to know, can it be used for industries producing hazardous chemicals?
What chemical?
Hazardous, like strong, high COD, BOD chemicals, hazardous chemicals.
Hazardous chemical. Yeah, we think we need to add the RO membrane. And the iron membrane is very important to remove some ions, just like the hazardous chemicals.
Okay.
We can through the RO membrane, yeah.
Okay, so it can remove it. We've got another question from Mr. Deepak Hebal, who would like to know, in one of the slides, it shows the system mounted on a boat and utilizing river water. What is the permissible salinity and turbidity of water quality for treatment?
Okay, the salinity we can treat like the seawater salinity, and the turbidity is maybe below the 500 NTU.
Below 500, okay.
Yeah.
Okay, I think we've covered most of the questions for this section then. Thank you, William. That was an excellent presentation. If all our participants, if you have more questions regarding the QWater, please do reach out and we will try and answer as many questions and get back to you on the system. So thank you, William. Thank you for taking time out and presenting this QWater system. For our next session, we are going to be discussing the AIoT, which is your intelligent IoT systems, which ITRI the water division at ITRI have developed for wastewater treatment and for your water treatment solutions with the intelligent platform for monitoring the whole thing. And joining us for this session is Dr. Wayne Lowe. Hello, good afternoon, Dr. Lowe. Thank you for joining us. Dr. Lowe has received his PhD from the University of British Columbia, Canada. He's a senior engineer at the Water Division and has over 20 years of professional experience. His recent area of focus has been on the digital transformation of the water industry. And his research has even won an IoT Innovation Award from the Pan Wen Yuan Foundation in Taiwan. And his work has also resulted in an innovative startup company based in Taiwan. Dr. Lowe, thank you for joining us this afternoon, and over to you. Thank you.
Can you hear me? Can you hear me clearly?
Yes, we can hear you clearly, Dr. Lowe. Thank you.
Okay, I think you cannot see me, right?
No, we can't see you, no.
Okay, good. Yeah, I just heard about in India, you eat lunch at around 2 o'clock, right?
It depends. 2 o'clock. I think between 1 and 2 is our lunchtime. So
Okay, good. Yeah, we
we're
eat
not
lunch
lunch hour yet. So,
sharp at noon, 12 o'clock. So I think now is, I still can say good morning to friends in India, right?
yes, we're still in good morning. Yes, it's good afternoon in Taiwan, but we're still in the morning session in India. Yes.
Okay, good. So I think I will try to make my presentation clear and short. Then it don't affect your lunch time. Okay, just as you said, today my topic is smart control of water wastewater treatment. Especially I want to focus on AIoT application. IoT, Internet of Things, I think more or less people know about this. There are 3 layers in IoT. The first one is sensing layer. The second one is data analyzing layer. And the last one is application layer. I think the most important thing is we use interconnection to connect things together. So in this system, we don't need human being to do something for the system. So you sense the signal and you transfer it to the cloud, and then you can show it on your display. So it's smart. This slide, you can see different kinds of dashboard. It's vivid, huh? So you can see a lot of information on those screens. I think this is the most important thing of IoT nowadays. People collect information, collect data. But in many times, data is meaningless for people. But using those dashboard, we can turn data to meaningful information. So it's easier for people to understand. And now we introduce another idea. Another word is IoT. What's the difference of IoT and IoT? I think there is one I in the middle. And IoT is Internet of Intelligent Things. That is, if we link those things together, and those things, they are able to do something to respond to the change of the environment, then it becomes an intelligent thing. So we put them together, we interconnect them together, we call it IIoT. For IIoT application in water industry, I think there are 3 I are very important. 3 components of I are very important. The first I is instrumentation, such as DO, pH, ORP, those sensors. The second thing is interconnection. It can be wireless or with wire. And the last thing is intelligence. Because of we have to transfer data from thing to thing. So a fixed IP is very important. That is, if without a fixed IP, you don't know where your data goes. And beyond this, we add another two things in our system. One is online sensing. The second thing is real-time control. So under those components, we make our system not only IoT system, it's an IoIT. After we put sensors in our system and we collect data, so we can form a big data. I think those big data in nowadays people use it for visualization to show those data on the dashboard or display to make it as information. But we want to do more. We want to explore the value of those data. And also we want to apply, we want to do some application of those data. So we call it, we move it from IoT to intelligentization. That is, the system, it can sense the change of environment. And also it can memorize and it can do some adjustment. It can learn and it can do adopt. This is the beauty of big data. So especially we want to focus on a new technology, AI, artificial intelligence. So we put AI and IoT together, it becomes AIoT. Nowadays in water industry, still some problems need to be solved, including the first thing is we have to reduce the abnormal discharge. In another word, to make effluent more stable. Also, we have to reduce the energy consuming and the material usage of water treatment. Then reducing the input of human power and reduce the human error are also important. The last one is, this is the need and also the threat of digital transformation, including recording the operation conditions in a water treatment plant, including reporting and management. In this area, I think the key technology we use, including three important areas. The first one is water technology, water treatment technology. The second thing is SCADA and also IoT technology. The third thing is just like I mentioned, big data and the AI application. Okay, the features of IWater. We not only do automation, we are moving towards from automation to intelligent, from A to I. And how we do it, I think later on I will introduce more about this. We use SRP. What does SRP stand for? It's Solution Ready Package, not only a component. It's a package, including sensor, including IoT gateway, including interconnection, probably as well as also including the device we want to make some change to control our system. So we use SRP to serve water purification, municipal wastewater, industrial wastewater, agricultural wastewater, water reclamation, and also we make seawater to sweet water. Then we use an intelligent management platform with a visual display to provide the function of monitoring, remote control, and the supervision management. We are using IT to enforce, to support OT. IT is information technology, OT is operation technology. Many people, they heard about AI, they worry about they are losing their jobs. Actually, we use IT to support. We are not using IT to replace OT. We use it to make people have a better working environment in their water and wastewater treatment plant. Okay, then I'm going to talk about from A to I. That is from automation to intelligent. I think PLC is widely used in water and wastewater treatment plants. Probably more than 98% of the plants use PLC to do automation. PLC is very stable, cheap, and also, you know, it can do repeating things. So it's easy to apply it to do automation. But when doing this kind of automation, normally the operation condition is decided by engineers. When they do design or they do the test run, they have already make a default value into the PLC system. But is that value, is that the value setup point, is that the best condition for water or wastewater treatment plant? I would say probably no, because the influence of water or wastewater is always changing, including quality and the quantity. So under that condition, it's not easy to use just single condition to operate all the different kind of influence. The best way is we have already put sensor into different unit. We collect the change of influence, water quality and the quantity. So we send a signal to our database and use the data from database to calculate. And we can have a better operation condition. We send this signal back to PLC and change the setup point. So now we can change the operation condition by the various of influence. I think that is how we call it from A to I. We make the automation more smart. Probably some of you, you wondered about why we can use AI for water treatment. I think there are two main reasons. The first one I have already talked about it is virus of influence. So to overcome this problem, I think in university or in college, our professor teachers always teach us you have to consider about safety factor, because your influence is changing, so you have to consider about safety factor. So from engineering side, you put safety factor everywhere, and from operation side, also you want to guarantee the water is you can fit the discharge requirement. So you put more air into the reactor, you add more chemical into the reactor, it ends up it's over design plus over operation. So you lost a lot of money. The second thing we think we can use AI is because of the models now we use, we do the function design, we calculate, we determine how large the facility we want to build. We use theoretical models. And this model is very complicated. Take biological treatment as an example. Now I think the activity search model number 3 is the most popular one, widely accepted by university, by engineers, and many different situations. But it is very complicated. Take for example, it including 21 biological process and also 49 parameters, more than 100 coefficients. So if we want to handle this model, it's not so easy. And the result of the prediction is also not so good. But if we use data science, then we can solve those two major problems. AI machine learning, we can put different kinds of data into as our input layer. We can put it into our hinder layer. Hinder layer normally is algorithm, a model to calculate, to do some algorithm for your input layer. And then it comes out output. This output can be minimization, can be optimization, or optimization, or a certain value. So you can set up an objective value for this system. So by using this model, so we can do some prediction or some application of automation for water treatment. Okay, the next slide shows different algorithm for AI, and includes probably more than 30 kinds of tools you can use, and I think most of them are open source, so you can find it from the internet. As a wastewater engineer, we don't have to be an expert of AI algorithm. We don't have to know each one of them. I think you just have to know which one is good for your simulation is okay. In water and wastewater treatment, this area, I think probably you know 4 or 5 of them, then you can handle it very well. Okay, this slide is a typical water treatment process in our society. So we can see in front, and the water goes through primary clarifier, then biological treatment, secondary clarifier. If you want to make the water cleaner, so you can add coagulant into the water, and after the sedimentation, you can have a better water remove SS. If you want to have high quality of water, probably you apply membrane filtration to your system, so you can have water, you can reuse it. I think this is a simplified, a typical process of water treatment, including wastewater treatment. And we choose some places to develop SRP, solution ready package. So we choose some places such as inlet pump, and also aeration machine, blowers, biological treatment. I think probably 70% of water and wastewater treatment plants use biological treatment process or unit. And also calculation, SRP. The last one is membrane filtration. Okay, stages of smart water control. The first step, I think you can build a reachable command center. We go to plant, and we give some suggestion, which kind of data you want to collect, which kind of information you want to show on your dashboard. So then we come back and we make a big data through the SCADA system, and then we design a dashboard. So it's a customized. So we discuss with our customer, then we make a dashboard, a system they need. This is the first step. After the first step, we have already collected data. And those data from big data, the next step we can consider about use those data, and through intelligent software, we can make a smart control of the system. We send the signal back to device, so we can change the device. Of course, you have to make some change of your device. If your motor, your pump is fixed speed, fixed frequency, then it's not easy to do smart control. You have to change it as a various frequency device. Okay, after that, we can move to the third stage. In this stage, we can do whole plant in intelligent system. We integrate unit SRP, utility, and also manufacturing systems. We add those information together, make it a platform, so we can do a whole plant intelligent system. So in this smart control, we can apply public cloud, and also we can use private cloud. It up to the customer which kind of system they are using. I think now I'm going to give you 2 examples of how we use those smart control SRP to our real plant. The first case I'm going to talk is about we use AI model to predict the biological treatment effluent. The second one is how we use AI to do smart control of accurate dosage of chemical for a drinking water purification plant. The first case is this plant is an industrial wastewater treatment plant. It includes 4 anaerobic bioreactors plus 2-stage aerobic bioreactors, and we do the prediction for anaerobic bioreactor, the effluent of aerobic bioreactor, and also aerobic bioreactors. The input layer we put into our system, including the data from online sensor. I think that is the basic one. And also we collect data from lab, the lab water analysis. We also collect the data from the lab. We do some data retreatment. We make the time interval, make it even, so we can feed those data into our hidden layer. And also we have data gained from data treatment. In total, more than 200 items were taken as input fusion. And the AI algorithm we use is SVR, supporting vector regressions. Okay, the output layer, including COD, SS, VA, volatile acid, and the PA. PA is partial active alkalinity. Okay, and this model, this system, the function we want to do the purpose of this model is we can predict the effluent quality 6 hours from now. So we know if it exceeds the limitation, it gives you a warning. So you got an early warning. And also, if you know there is a risk of your abnormal discharge, then the system also suggests you some strategy how to respond. And also it can do smart control. Okay, this slide is the dashboard. We show the current data of the whole plant. And we use different color to distinguish the condition of different unit. For example, green is safe. Yellow is you have to pay attention to it. The red is exceeds the limitation. This slide is the curve of real data and also prediction data. So you can see the green line. Sorry, yes, the green line. The green line is current data. It's measured data, and the orange line is predict data. You can see 2 lines, they fit each other, they link to each other. So the prediction result is not bad, it's very acceptable. COD and also SS. Then we can also see VA over PA because it's an aerobic digester. So volatile acid and also alkalinity are important for the system. So we also do some prediction for this system. So you can see the situation of those 2 lines. They're close to each other. And from SS, this paragraph, you can see there is a red line at 300, SS 300. It means the limitation. If you over this line, then the system give you a red light like this. If you under that line is green light, if over is red light. And once you got a red line, probably you like to click at the bottom of this suggestion, suggests you what you can do to solve the problem, to reduce the risk of no more discharge. So this is the system of an example. We use AI to do prediction. Of course, if your condition is over the limitation line, the system also can do AI calculation and also smart control to change the operation condition. So the prediction value can return to under the limitation. The second example is calculation, sedimentation, SRP. We use it in drinking water purification plant. This plant is not big. It treats 4,000 cubic meter of water per day. Because it's small, so the owner, they don't want to put too many human power into this plant. Before they use 2 operators in this plant, but they want to reduce it. So we go there and we check the whole plant. We talk with the operators and we give some suggestion. Okay, so in a traditional way to determine how much chemical to add, calculate to add into the water to remove turbidity, we use jar test. So we have a raw water and we add different amount of calculant into those jars. We do fast mixing and followed by slow mixing. Then we put it still for 30 or 1 hour. We use a meter to measure turbidity. And which one is the smaller? So that is the chemical, the amount of chemical we add into the water. And this test takes around 2 hours to do it. So every day you do a batch of this test, you can also get a result to change your dosage of the water. But we decided to use AI to replace this kind of work. The input layer we use is turbidity, water flow, pH, and also the chemical dosage, steaming current, and so on as our input layer. In the next slide, we can see we also change the dosing pump. Before it's a dosing pump adjusted by human power. The operator have to adjust the dosage every day, but we change it as a various frequency dosing pump. So it can accept the signal from our server. So the computer can control it without a human being. Okay, this is the result. The blue line is dosage from 2018. The chemical is added by operators. And the orange line is our AI smart control. So we can see it become more smoother. And also we reduce the dosage of chemical. From this table, you can see we saved the chemical dosage up to almost 20%. And for this plant, I think we also fit the requirement of the owner. They want to reduce human power input, and we can do that. With this system, it's possible to reduce the person, reduce from 2% to 2 hours per day. That is, people don't have to stay there for a whole day long. You have to go there every day, 2 hours to check every situation, whether it's in a good condition, that's okay. In Taiwan, in Hsinchu, we have a remote control center. And this remote control center, we collect different data from pilot and the full-scale smart control plants in Taiwan. So in Hsinchu, we can see more than 10 plants operation condition from all over the Taiwan, not only in Taiwan because it's IoT. So through Wi-Fi, we can also got information from overseas. We have 4 pilots in India, in your country, 3 in Chennai, and 1 in New Delhi. Okay, and this slide is the dashboard from Chennai. It's a MBR pilot. Okay, I think close to the end. With this smart control, we can serve wastewater treatment, drinking water treatment, water reclamation, and also collecting system. I think it's an opportunity for water industry, and also it's a big opportunity for this business to move to the next stage. Thank you for your listening. I think I also put my email here. If you have any question, you are welcome to contact with me. Okay, thank you.
Thank you, Dr. Low. I think that was very, very interesting to see how developed the whole thing, and it's like how you summarized it. I think it's the need of the hour right now, especially given the whole situation of social distancing, and especially in India, we had to have a sudden lockdown, and a lot of the plants, they had to have sudden shutdowns that came into place. But if we had systems like this already in place, a lot of the ETPs would have saved a lot of money from sudden shutdowns and not being able to access to maintain all the membranes and the systems. So this is it's very, very interesting. So thank you. And to all our participants, we can now take some questions as well. I'm sure you have many questions for Dr. Low. We already have one from Ms. Nisha Priyamani, who would like to know, is AIoT used in surface water reservoirs to monitor health of water bodies?
Okay, I think IoT, the purpose of IoT is in water industry. I think you put sensor in different situation, and then you collect data. After you collect data, then it's how you want to explore some information from those data. So it's possible. For instance, if you know the water reservoir, I think we concern about our pH. We concern about probably stability, and also if your sensor can sense some heavy metal or something, it's possible to know the water quality in water reservoirs. So just like you said, people don't have to go there, take a water sample back to the lab to analysis. Using those data, one day, because it's online sensing, one day you can collect thousands, even 10,000s of data. And then those data, you can make some analysis, calculation. You'll be surprised what kind of result you get.
Yeah, that's true. And with that data, we can just redo it. Oh, she wants to know any examples. Have you done this before for any water bodies?
For water body, actually, we more focus on treatment plants.
Okay.
Yeah. But we are thinking about, to extend the project of water purification I just gave you as an example. We want to predict the raw water in reservoir. So in that case, we are going to collect some outside data. For instance, the data from government, not only from the plant. So we consider those data, or we can predict the raw water quality. And once we know the change of the raw water quality, for instance, after typhoon, after heavy rain, it become very dirty, then we know how to make a quick response, how much chemical we are going to add. And probably you have to open another stream more facility to treat those kind of raw water. This is our next step we want to do.
Okay, this is really interesting. So basically, so on all this data, you're able to create predictive models and generate, on how the system is going to behave, and then but how long does it take, for instance, like you say, you have for the pump, the system knows how to, what dosing chemicals. How long for it to behave in that intelligent way, for the algorithms to kick in? Does it kick in? Does it take a lot of while for it to get intelligent enough to operate the system on its own? How much data does it require?
How much data? Okay. First, if we can use online sensing data, actually, how to explain? There are two ways we use smart control. One is we use the data from data bank, big data. And I would say it's better to cover the whole year because of the season change. The best situation is to cover at least 3 years data. I think that is because machine have to learn different kind of situation. More data you have, your AI is smarter. You can do a better job. Another thing is we try to reduce the data amount. We use the current change, the rate of the change to control the system. So under that case, we don't need historic data. We only have to know the change of this time. So there are two ways to do it. And we have successful case of both methods.
Okay. So I'm just going to repeat myself, perhaps, and maybe ask again. But so supposing, we have an ETP facility over here, and they want to install, the solution ready package at any one part of the one part of the unit. If they want to do it, they can have this the system performing would you have to collect the sensor data over a long period, over like a few months, and then you can design the package, or you just need some historical data, like 1 year data or something? You'll have to have an online sensor collecting data.
Okay. I think because each plant is different from another, it's very different. So it's better to use the data collect from this plant, not use the data from some other plants. So what we do is, if we have 3 months of data, then we developed an AI model. And with this model, we will set some limitation. You can use only for the data range within those 3 months, because machine they never met a situation of the condition out of those data. Yeah. But after 1 year, after 2 years, then we will gradually to change, to adjust our limitation, because the machine now knows something, so it knows how to respond to those situations. Okay. So the system is not a one-time system. You have to do, of course, you have to do machine retrain. You use new data to retrain your machine and make it more suitable for your facility.
Okay, so we have 3 months of sensor data, put in get the machine to work within those limitations, and we can keep retraining it to increase our parameters and working better and improving performance. So it would take so then it should, within a year, it should be stable enough with a good performance. I think it would depend on the ETP as well, on how wearing the water quality is, I imagine. It depends.
Yeah, another thing I want to add is the quality of data you get from the matter is very important. Garbage in, garbage out. And now we encountered many problems is the sensor, the meter cannot work properly to get good data for us. So for wastewater treatment, I think that is still a problem we are going to fix the problem. For clean water, for water reservoir or water purification, this kind of problem is okay. It's not so serious. But for especially industrial wastewater, you have to be very careful of the data you collect.
Yeah, that's true.
Right.
Especially, yeah. Okay. So thank you, Dr. Low. I think that was very interesting.
Thank you.
Thank
Yeah.
you. I think that was an extremely very interesting session, and I think IoT with IIoT, this is the future. So this is going beyond. I think this is taking Industry 4.0 to the next level, really.
Right.
So thank you, and thank you to all our participants for joining us. If you have any more questions, you could reach out to Dr. Low on the email he mentioned, or you could even reach out to me and we could try and answer your queries that you have. So thank you, everybody. And thank you to, we at Cercin Technologies would like to also thank the ITRI team, especially Dr. Juang, who has helped, to coordinate and organize this 4-part webinar series, which has helped showcase all the innovative technologies which have been developed by the ITRI Water Division at ITRI. Given the whole lockdown situation, I think at least this way we've got a good insight into what is being developed through this online portal being developed at ITRI, and a lot of people are also piqued a lot of people's interest. So thank you to all our wonderful participants for joining us. If you have any queries on all the technologies that have been showcased, you want to chat about it, how you can incorporate it and integrate it in your facility, please do reach out and we could schedule a call. So thank you again, Dr. Low. Thank you, William. Thank you, Dr. Juan. Thank you, everybody. Bye-bye.
Thank you. Bye-bye.
Bye.